The Mushroom and the Fire, Food Science and Thermal Physics Record, written by Cardinal, the illumination of a dynamic archive. This record observes how certain forms of nourishment require transformation before they can enter the human body, and how heat functions not as destruction, but as translation between biological systems shaped by different needs. This record is not a warning, an argument, or an instruction. It does not seek to persuade, defend, or correct. It exists to observe how a common food behaves when examined at the level of structure rather than habit. Mushrooms appear familiar and edible, yet their internal composition resists the human body in ways that are not immediately visible. What is held here is an account of how preparation alters compatibility, not by adding value, but by allowing value to be received. The record does not elevate tradition, efficiency, or preference. It simply follows what occurs when fungal biology meets human digestion under heat. In the places where mushrooms originate, they are not consumed. They work. They persist in darkness, dismantling what has already fallen, unlocking minerals held in wood and soil, and returning matter to circulation slowly and without display. Their bodies are shaped for endurance rather than tenderness, for resistance rather than surrender. When they are gathered and brought into kitchens, they arrive intact, still carrying the architecture that serves their original function. Entry into this record begins at that threshold, before cooking, where appearance suggests readiness but structure does not. Mushrooms do not belong to the plant world, though they are often placed there by habit rather than structure. They are fungi, a kingdom shaped by evolutionary pressures distinct from both plants and animals. Where plants grow toward light and animals move toward prey, fungi persist by remaining in place, performing slow biochemical labor over time. Their bodies are organized around endurance, resistance, and longevity, favoring strength over softness. This difference is not cosmetic. It determines how mushrooms behave in the environment and how they interact with other biological systems, including the human body. The outer walls of mushroom cells are composed largely of chitin, a rigid structural compound also found in insect exoskeletons and crustacean shells. Chitin provides firmness and protection, allowing mushrooms to maintain integrity in damp, decomposing environments where pressure, moisture, and microbial activity are constant. This material is not easily broken down. Human digestive systems lack the enzymes necessary to dismantle chitin efficiently, leaving these cell walls largely intact when mushrooms are eaten raw. Structure, not toxicity, defines the challenge. Within those chitin-reinforced walls exist amino acids, B vitamins, essential minerals, and water-soluble compounds capable of supporting human metabolism. The presence of nourishment does not guarantee access to it. In raw mushrooms, these nutrients remain enclosed within rigid cellular compartments, physically separated from digestive enzymes. They pass through the digestive tract present but unreachable, carried forward by a structure designed to resist breakdown rather than invite it. Raw mushrooms do not poison the body, but they demand effort without proportional return. The digestive system deploys acids, enzymes, and muscular contractions in an attempt to extract value from material designed to remain intact. Energy is expended while absorption remains limited. Digestion becomes labor rather than nourishment, not because the mushroom is harmful, but because its structure has not yet been translated into a compatible form. In addition to structural resistance, many edible mushrooms contain naturally occurring secondary compounds that serve the organism's own biological needs. These compounds support defense, communication, or environmental adaptation within fungal ecosystems. They are not designed for human digestion and offer no nutritional benefit in their raw state. When consumed uncooked, they enter the body intact, adding processing demand without providing metabolic support. These secondary compounds share a defining characteristic: they are chemically unstable under sustained heat. When exposed to cooking temperatures, molecular bonds weaken and configurations shift. Complex structures break down into simpler forms that the body can process or eliminate. This transformation does not occur through digestion alone. It requires external heat applied over time, acting on chemistry before ingestion begins. As heat is introduced, the mushroom does not lose nutritional value. It loses resistance. Structural barriers soften, chemical obstacles degrade, and what remains is the nutritional core. After cooking, the mushroom can interact with human biology without friction, not through disguise or force, but through compatibility. Nourishment becomes accessible because opposition has been removed. Mushrooms are composed largely of water held within chitin-reinforced cellular frameworks. When heat is applied, this water begins to migrate outward as internal temperatures rise. Steam forms as vaporization thresholds are reached and internal pressure increases. Shrinkage and softening mark the first visible signs of structural change, indicating that rigidity is giving way to release. As water continues to evaporate, rigid compartments collapse inward. Cell walls soften, membranes rupture, and internal contents are freed. Minerals loosen from binding sites. Proteins become exposed. What was once locked within durable architecture begins to circulate, not destroyed by heat, but liberated by it. Mushroom proteins respond to heat by unfolding slightly, a process that alters their three-dimensional shape without diminishing nutritional value. This partial denaturation exposes enzymatic access points, allowing human digestive enzymes to recognize and act upon them. What was once invisible to digestion becomes legible, translated into a form the body can read. Minerals such as potassium, selenium, copper, and phosphorus exist in mushrooms in meaningful quantities. In raw form, these minerals are often bound within structures that resist digestion. Cooking loosens these bindings, freeing minerals into states that can be absorbed efficiently through the intestinal lining. Availability emerges not from addition, but from release. As structural change progresses, aroma emerges. The savory scent that develops during cooking reflects chemical transformation rather than decoration. Sugars concentrate, amino acids react, and volatile compounds are released as moisture leaves the tissue. Smell functions as evidence, signaling that internal reconfiguration has occurred. When mushrooms are allowed to brown, Maillard reactions take place. These non-enzymatic reactions produce complex flavor compounds while also indicating that proteins and sugars have crossed into stable, digestible configurations. Browning marks a threshold. It signals completion rather than embellishment, transformation rather than appearance. Through these changes, the mushroom shifts roles. It no longer functions primarily as a decomposer adapted to resist breakdown in the environment. It becomes cooperative nourishment, capable of interacting with human digestion without opposition or excess demand. Its biological purpose changes through preparation. Cooking completes the mushroom's movement into food. It does not disguise flaws or introduce safety through concealment. It resolves incompatibility by finishing the transformation that raw consumption leaves incomplete. The work is done before eating begins. Across cultures and across time, mushrooms are almost always cooked. This pattern reflects accumulated observation preserved long before scientific explanation. Knowledge traveled through practice rather than theory, carried forward by results that could be felt and repeated. Modern trends promoting raw mushroom consumption often apply plant logic to organisms that do not share plant structure or chemistry. This misalignment overlooks fungal biology and the role of preparation in nourishment. Familiar appearance masks fundamental difference. When cooking is skipped, fewer nutrients are absorbed and more energy is spent processing resistant material. The body works harder and gains less. Inefficiency replaces support, not as a dramatic failure, but as a quiet imbalance. Heat does not act violently in this exchange. It acts as a translator, converting fungal biology into a form the human body can recognize and use. It bridges differences shaped by separate evolutionary paths without forcing adaptation from either side. Cooking mushrooms acknowledges difference rather than ignoring it. Nourishment occurs through accommodation instead of force, aligning structure with digestion rather than demanding that the body adapt to resistance. Once cooked, mushrooms offer depth, mineral support, and metabolic nourishment with little demand in return. The labor has already been completed externally. What remains is cooperation. When the mushroom softens, browns, and releases its scent, it crosses a threshold. It is no longer resistant matter shaped for decomposition. It becomes food. What has been observed here does not resolve into instruction or recommendation. It notes how compatibility emerges when preparation completes what structure withholds. The mushroom remains what it is. Only its relationship to the body changes. Long before explanations were named, heat mediated the relationship between human bodies and the world they consumed. In mushrooms, that mediation remains visible each time fire finishes what structure began. Some records exist to remember posture rather than to teach lessons. This record is preserved as part of a living archive to maintain continuity of observation. It documents how preparation functions as an interface between fungal structure and human digestion, noting how heat, time, and restraint allow nourishment to occur without excess labor. Food Science and Thermal Physics Demonstration, page 31. Thermal translation of Cremonine mushrooms. Material components, observed system, fresh Cremonine mushrooms, Agaricus bisporus. Neutral cooking fat as lipid-based thermal interface. Sodium chloride as ionic enhancer. Intracellular water retained prior to heating. Process demonstration. Heat is introduced through conductive contact between the mushroom surface and a heated substrate. Thermal energy transfers inward, increasing molecular motion and destabilizing chitin-based structures. A lipid medium distributes heat evenly while moderating dehydration. As internal water reaches vaporization thresholds, steam pressure initiates cellular collapse. Proteins partially denature, secondary compounds degrade, mineral bindings loosen, and non-enzymatic browning signals completion of molecular translation. Demonstration outcome. This preparation does not add nourishment. It removes opposition. Heat acts as mediator. The mushroom remains what it is. The relationship changes. Thank you for visiting our channel and spending time with our work. Red Cardinal Kitchen, the illumination of a dynamic archive.